All right, in section 4.2, we're going to review logarithmic functions. The two objectives we're going to look at in this section will be objective 1, determine if two functions are inverses of each other, and objective 2, we're going to look at how to use some of the properties of logarithms. That'll make our life in calculus a little easier. So let's review this information from college algebra. You know, in college algebra, you probably talked about one-to-one functions. A function is said to be a one-to-one function if for any elements a and b that are in the domain of f, and they're not equal, so a does not equal b, that implies f of a does not equal f of b. That is, what the definition of a one-to-one function is. And you might remember, a visual way of looking at this was called the horizontal line test. That if you have a graph of a function and any horizontal line you draw intersected the graph in only one point, then we said the function was one-to-one. So if you have two one-to-one functions that let me just generically say, are f and g, these two one-to-one functions f and g are inverses of each other if when you do the composition f of g of x, you get x for every x that's in the domain of g. And when you do the composition g of f of x, you also get x for every x that's in the domain of f. So if f is a one-to-one function and g is its inverse, the thing that's kind of neat is that the graphs of f and g, they're going to be reflections over the line y equals x. So, they're symmetric. The graph of a function and its inverse function are symmetric about the line y equals x. And again, all of this should be reviewed from college algebra. Final review topic is only one-to-one functions have inverse functions. So laying all this foundation about inverse functions because, we're going to see here in this section, we're going to review the fact that the logarithmic function is the inverse of an exponential function. So let's look at this first example. Let's show that the functions f of x equals x minus 8 over 4 and g of x equals 4x plus 8 are inverses of each other. So write this down. I'm going to head off to the chalkboard to show that these functions are inverses of each other. Hey folks, in this example we're asked to show that the functions f of x equals x minus 8 over 4 and g of x equals 4x plus 8 are inverses of each other. So we need to find compositions in order to make sure that that is true. So remember, if f of g of x equals x and g of f of x equals x, then we know they are inverses of each other. So let's start off by finding f of g of x. Well, that would be f of 4x plus 8. So to find the f of 4x plus 8, we take 4x plus 8 and we toss it into function f where we see x. So we have 4x plus 8 minus 8. And we'll see that simplifies to 4x over 4, which equals x. So f of g of x does equal x. But we also have to do g of f of x. Both compositions have to equal x in order to claim they are inverses of each other. So here, what does that give us? G of f of x, x minus 8 over 4. To find the g of x minus 8 over 4, we take x minus 8 over 4 and we toss it in here for x into function g. So that gives us 4 times x minus 8 over 4 plus 8. Let's see if we multiply here. Well, the 4's cancel out. So we're left with x minus 8 plus 8, which simplifies to x. So since f of g of x is x and g of f of x is x, we can now conclude, yes, these functions are inverses of each other. So let's head back to the slides and see what is next. All right, those functions were inverses of each other because when we did the composition f of g of x, we ended up with x. And when we did the composition g of f of x, we ended up with x. All right, we say that y equals log base b of x if and only if b to the y is equal to x, where b is greater than 0, b is not equal to 1, and x is greater than 0. So you may have seen this in the past math class of logarithms and exponentials. It really tells us how to go from logarithmic form to exponential form and vice versa. I could say that that first statement, it's an if and only if statement, I could say that is actually the definition of a logarithm. And again, you might have seen that in a previous class, which is fine. Let me also stress that the expression, that you see there, I read it as the log of x base b or the log base b of x. Probably most of the time I would say log base b of x. But it's also acceptable to say the log of x base b. So let's check out this example. We're going to fill in the table and sketch a graph of each function. So there's the table. So we have the function f of x equals 3 to the x. And then the other function g, is log base 3 of x. So write this down because I'm going to head off to the chalkboard. I'm going to reproduce this table and we'll fill it in. And then we'll sketch the graph of each one of those functions. All right, folks, in this example, we're asked to fill in the table and then sketch a graph of each function. We have the function 3 to the x, and the other function is log base 3 of x. I wrote up here in yellow kind of like a definition of a logarithm that you might have seen in a prior algebra class. Y equals log base b of x if and only if b to the y is equal to x. That definition of logarithm shows us that logarithms and exponentials are the same. That if you know an exponential equation, you could write an equivalent logarithmic equation, and vice versa. So, well, let's continue here. X is -2, so we'll put -2 in for x, and we get 1/9. Put -1 in for x, we get 1/3. Put 0 in for x, and we know we get 1. Put 1 in for x, we have 3. And put 2 in for x, and we get 9. Okay, now here, 1/9 comes in for x. So we have log base 3 of 1/9. Well, what does that equal? Well, because, and I have this written strategically, we know 3 to the -2 equals 1/9. Look at it here. 3 to the -2 equals 1/9. That means I can write it as log base 3 of 1/9 equals, well, what was y? -2. Log base 3 of 1/3. Because 3 to the -1 is 1/3, that's the exponential part. The logarithmic part is log base 3 of 1/3. Log base 3 of 1/3 equals the exponent, -1. Here, log base 3 of 1. Well, log base 3 of 1 is 0. I'm just using this again. I have all the information I need here to fill this in. Log base 3 of 3 is 1, and log base 3 of 9 is 2. So let's graph these. So I'm going to graph f of x first. So let's see, we'd have 0, 1 on the graph, 1, 3 on the graph, 2, 9 on the graph. That's off the board. Negative 1 is 1/3. So let me graph this. There's the graph of f of x equals 3 to the x. Okay, so now let's graph log base 3 of x. So let's see, let me start with this one. When x is 1, y is 0. So let me plot that point. When x is 3, y is 1. When x is 3, y is 1. When x is 9, well, that's off my board. But when x is 9, y would be 2. Let's see, x is 1/3. Y is negative 1. I'm sorry. You probably already noticed that I forgot my negative sign there. When x is 1/3, y is negative 1. So 1/3 negative 1. I'll say that's about right here. When x is 1/9, y is negative 2. I'll say that's about right here. I'm going to graph it now. This is the graph of g of x equals log base 3 of x. Now let me use this blue chalk to sketch in the line y equals x. This is the line y equals x. Notice the graph of 3 to the x, the graph of f of x equals 3 to the x, and the graph of g of x equals log base 3 of x. Notice how they're symmetric about the line y equals x. It's a mirror image, but if I fold it across this blue dashed line, they would match up with each other. That is a distinguishing feature of very important functions that are called inverse functions. A function and its inverse function will have graphs that are symmetric about the line y equals x. So for the exponential function 3 to the x, its inverse function is log base 3 of x. So exponential functions and logarithmic functions are inverses of each other. But let's head back to the slides and see what more we're going to review about logarithms. All right, in that last example, we saw that those functions, they appeared to be inverses of each other, and that's because the logarithmic function is the inverse of an exponential function. The actual definition of a logarithmic function is, there it is, f of x equals log base b of x. B greater than 0 but not equal to 1, and the domain of the logarithmic function is parentheses 0 to infinity. Another way to think of the domain is you cannot take the logarithm of a negative number. Now in the world of logarithms, you may remember from college algebra, there are two biggies. The common log. Common log has base 10. But we don't write it as log base 10 of x. We just simply write it as log x. So you just see log x, it's understood that the base is 10. And the one that we are going to deal with exclusively is the natural log. The natural log has base e. Now we don't write that as log base e of x. We write that as ln x. That represents the natural log of x. And let's quickly review some properties of logarithms that, again, you would have seen in a prior algebra class. There was one called the product rule. That says if you have the log base b of the product m times n, you can rewrite it as the sum, log base b of m plus log base b of n. There was one called the quotient rule. that says if you have the log base b of m divided by n, you can rewrite that as subtraction. Log base b of m minus log base b of n. There was one called the power rule, that if you had log base b of m to the n, that you can move that exponent out front of the log statement and rewrite it as n times log base b of m. Okay, now the inverse properties that says b raised to the log base b of x equals x, and log base b of b to the x equals x, those two properties are a direct result of the fact that b to the x, the function b to the x, and the function log base b of x are inverses of each other. So if you have f of x equals b to the x and g of x equals log base b of x, and you do the composition f of g of x, and you do the composition g of f of x, both those compositions have to end up being x because they're inverses of each other. And just, I don't know, like I said, this is general properties. I guess these are a couple of quick facts. Log base b of 1 is 0, so it doesn't matter what the base is. Natural log of 1 is 0. And log base b of b is 1, and it doesn't matter what the b is. And then this thing called a one-to-one property, I also refer to it as the preservation of equality. Log base b of m equals log base b of n if and only if m is equal to n. So I know you've seen all this in a prior algebra class. I just wanted to kind of quickly review it. Now let's check out an example. So this is like old algebra, but let's use the properties of logarithms to rewrite the following. 3 parts. Part A, we're going to rewrite log of 12x. Part B, we're going to rewrite log base 6 of the quantity 13 over 19. And in part C, we're going to rewrite the natural log of the 4th root e over 2. So write these down. Going to head off to the chalkboard and work through these. All right, folks, we just reviewed a lot of laws and properties of logarithms. So this example, we're asked to rewrite the following. So this is kind of like using everything we know from that prior college algebra class and what we just reviewed to just rewrite these expressions. So in A, it was the log of 12x. Okay, folks, that's a product. The log of 12 times x. So I can use that property that says I can rewrite products as addition. So I'd rewrite this as the log of 12 plus the log of x. And that's it. Remember, there's nothing written here as a base, so this is a common log. We know that the base is understood to be 10. But that's it for A. In B, we have the log, base 6 of 13 over 19. So I use that property of logarithms that says when I'm taking the log of a quotient, I can rewrite it as subtraction. So this one would simply be log base 6 of 13 minus log base 6 of 19. That's it. Here we have the natural log of the 4th root of e over 2. ln 4th root e over 2. Remember, natural log means that the base here is e. So now here the first thing I have to do is rewrite the 4th root as a rational exponent. So the 4th root is rewritten as an exponent of 1/4. Then I use that property of logarithms that says, hey, I can take this exponent and put it out front. And so I have 1/4 natural log of e over 2. Now I use the property that says when I have the logarithm of a quotient, I can rewrite it as subtraction. So this is 1/4. And I better put down a parenthesis so I don't make a careless mistake. So the natural log of e over 2 is the natural log of e minus the natural log of 2. And we're not quite done. We're almost done. I see the natural log of e here. Remember natural log, the base is e. So it's natural log, the base is e of e. This simplifies, the natural log of e simplifies to 1. And that's as far as I'm going to go with it. So just to practice a little bit to make sure you're remembering all these rules and properties of logarithms. In section 4.2, pause the video, go to the exercises in section 4.2, do numbers 30 and 32. After you do them, restart the video. I'll be here at the board working through them. All right, folks, at number 30, you were asked to use those properties, etc., to rewrite log of 17 times 11. So, quite simply, this product can be rewritten as the log of 17 plus the log of 11. And that's it. In 32, it's the natural log of the cube root of 11. Well, the first thing I would do is rewrite the cube root as an exponent of 1/3. So cube root of 11 is the same thing as 11 to the 1/3. And then there's that rule of exponents that says, the rule of logarithmic exponents says you can bring the 1/3 out front. And that's it. So hopefully you got those two. Hopefully this is all coming back to you from algebra, these properties of logarithms. But let's head back to the slides and see what's next. All right, we have one more example I'd like to look at using some facts of logarithms. And this is, basically reviewing how, we can take exponential equations and rewrite them as logarithmic equations. Or vice versa. You could take a logarithmic equation and rewrite it as an exponential equation. So here, 3 different exponential equations. Part A, 3 to the 4th equals 81. Part B, 5 to the negative 2nd equals 1 over 25. And part C, e to the 0 equals 1. So write these down because I'm going to head to the chalkboard and we're going to rewrite each one of these equations as an equivalent logarithmic equation. All right, however, I've already used this knowledge, this information, in a prior example when we were coming up with the graph of g of x equals log base 3 of x. But I thought we'd do one more example where we rewrite an exponential equation as a logarithmic equation. This is just using the definition of a logarithm. So this is the exponential equation. 3 to the 4th equals 81. So as a logarithm, that's log base 3. Notice the base of logarithm has to be the same base as the exponential equation. So 3 to the 4th equals 81. That matches up with log base 3 of 81 equals 4. So going from exponential to logarithmic. You could also go from logarithmic to exponential. Part B, 5 to the negative 2nd equals 1 over 25. So that would be log base 5 of 1 over 25 equals negative 2. Part C. Now part C, we might be tempted to say, oh, this is log base e of 1 equals 0. But remember, we don't write down log base e. Instead of log base e, we say the natural log of 1 is equal to 0. So I just have a couple of these for you to practice. So section 4.2 exercises. Try 35 and 37. So pause the video, try these two. After you've done them, restart the video, and I'll be here at the board doing them. All right, at number 35, you were asked to write, or to rewrite the exponential equation 2 to the 5th equals 32 as a logarithmic equation. So that would be log base 2 of 32 equals 5. That's it. 37, rewrite the exponential equation. 2 to the negative third equals 1/8 as a logarithmic equation. So that would be log base 2 of 1/8 equals negative 3. So that's it on this section where we did a very quick review of everything you would have already learned about logarithms. So at this time you can do the exercises in section 4.2. So go do them. Go do the exercises in section 4.2. Thanks for watching.